referring to it, then what can be the possible challenges? Here I have mentioned the four major issues, but this is not the list that you can say it is not the only four. There are others also that pertain to a different application from, and in one application it may be, in another it may not be. First issue is the of the high dimensionality. Let's say we want to describe a drug by its you can say the chemical properties, then the dimensionality of that vector is going to be very high. Similarly, let's say we have the gene expression data, then the number of genes can be around 4,000, maybe 20,000, and the number of samples happen to be quite low in those cases. And first issue is like how we are collecting that. Whenever we are dealing with the gene expression data sets, it means we are dealing with either the microorganisms or the macroorganisms. First thing. Then the another issue is like the sample size is going to be very small, first thing, and the sample size is also differ from one condition to another condition. Now, what does it mean actually, the condition? Whenever we are collecting this type of biological data, then we have to do it under a controlled environment. Whenever we see the controlled environment, then for an example, let's say we have to maintain a specific temperature, a specific humidity, some kind of you can say the light, and all those things we have to consider. Let's say the required temperature range for that experiment is around 20 to 22 degrees Celsius. But if we are collecting the data even at 19 or maybe at 23, then that may not be useful for that particular application because the condition has changed, and depending upon the conditions or the parameters of your experiment, the behavior of genes may vary in terms of their expression levels. Then we have the last one. Actually, I have combined the second one and the third one. The last one is your multi-label behavior. Now, what does it mean? Then it means we have a single instance, and corresponding to that instance, the number of possible classes can be more than one. It may be 2, it may be 20. So that is termed as your multi-label behavior. From an example point of view, we can say, let's say we have a single drug, then the possible ADRs that may occur because of that drug, that may be large in number, maybe 10, maybe 5, maybe 20, that way. So that is termed as your multi-label behavior. It means one instance, but the number of labels are multiple. Now let's move to the first case study. It is not that generic, but for understanding point of view, like how biological data analysis can be useful, we have taken this study, and it is related to the prediction of drug functions using chemical and biological properties of drugs. First question arises like why we need to predict the drug function. Then here I would like to mention one thing, that whenever we have a disease and let's say we have to discover a drug for it, then our first choice is that whatever the number of available drugs we have with us, then is there any possibility to adapt any of the existing drug about which we are already aware. We are already aware about its side effects. We are already aware about its toxicity. We are already aware about its working mechanism. Everything we are aware. Then instead of identifying a new chemical component, whenever I am saying, then it means I am referring to the chemical, because drug is a chemical component that way. So instead of doing it from the scratch, that I will take this chemical molecule and then I will see whether it is going to be useful in a particular disease or not. If this is the scenario, then practically this is going to take lots of time and cost is even very high. Then before moving to this option, generally we used to repurpose the existing drugs. Reason being, we are already aware about those drugs and its property. Then we used to see whether the same drug can be customized, can be a little bit modified to another disease? If so, then the first step that comes under that category is the drug function prediction. Here, the drug function prediction that we have considered, it is actually at the, you can say more or less at the organ level. It may be further divided, the drug functions may be further have some categories, and maybe more abstract categories may also be generated, but that cannot be done like it's my own that I will take these categories. No, these are well defined mechanisms that are available, and this system, it can be downloaded from the PubChem databases. This information, entire information about the drug, is available at the PubChem databases. We have also taken it from there, and if you want to work in this area, then you have to refer to the standard databases, because this is not a field where you can generate your synthetic data. Anybody can collect the data and upload. No, there is a proper mechanism, standard databases from where you have to collect this data, because this is, if we have a drug and let's say this has been synthetically generated, but we don't have any idea whether that drug really exists or not. So we have to be very careful about the data collection and its processing while we are dealing this type of applications. Then the drug properties can be in different forms. First one is the chemical properties. Then a chemical compound, a chemical molecule, you can say, it can be represented either as a 1D structure. It may be like the in 2D or 3D. 2D like in form of an image, and 3D entire structure of that drug. And another representation can be of 17 molecular properties. This is more related to like how many number of hydrogen atoms are there, how many oxygen atoms are there, what type of bond they are relating in, what is the molecular weight of that thing. So this type of properties comes under 17 molecular properties. Here I will say that the chemical 1D structure is a simplified representation of 2D structure, and 2D is a simplified structure of your 3D structure. For 1D structure also, we have a number of works that have deal with the 1D structure, and these are quite performing the good way. 17 molecular properties and another class of chemical properties. So we can select 17 molecular properties plus any other 1D, 2D or 3D structure, the way you want to process it. Then other types of properties may be the biological property like the gene expressions, protein structures, pathways, and phenotypic properties like the drug reactions, adverse drug reactions, drug disease relationship, drug functions. So this is the overall working architecture of the work that we have done or the study that we performed, and it has been taken up as a sample to discuss about the biological data analysis. Here it can be seen that as an input we have two types of properties, chemical and the biological. Here in the chemical properties, SS refers to the SMILE strings. The name SS stands for the SMILE strings. It is a kind of 1D representation, a 1D vector representation of the drug molecule. Then we have the 17 molecular properties, sometimes referred as 17 molecular descriptor. That's why we have taken it as 17 MD. Then PS is the protein sequences, GEX is your gene expression data. When we, now let's move to the data first. Here it can be seen that the 4 different properties or the 4 different types of data that are actually representing the drugs we have collected, and SMILE strings, 17 molecule descriptors, and the drug functions. These have been downloaded from the PubChem database. For downloading it in Python, we have already done with, like you can say that we have a library and we can use it, that is PubChem Py. Another thing we have, for a customized thing, you can also write your customized query using that library that suits your application or your requirement. For the protein sequences, we have referred to the drug bank, again a standard database. And for the gene expression, actually gene expressions are not in any standard database, but it has been collected corresponding to different drugs through a project, LINCS project. Now this data is publicly available. One thing that you have to do, that the number of drugs may vary from PubChem to drug bank to LINCS project. So you have to map those drugs using the drug ID. Here it can be seen from table 1 that the number of drugs corresponding to your SMILE string property has been 7589. Then for 17 molecular descriptor again same, but for protein sequence the number of drugs is only 1179. For gene expression it is 959. Why so? In our standard database, we have around 14 thousands of drugs, one thing. But the properties, the in form of SMILE strings that is available corresponding to 7,000, approximately 7,500 drugs. But the protein sequences that have been collected and uploaded, it is available just around 1100 of the drugs. And for gene expression, as I mentioned, it was collected under a project, so around 9,950 samples have been taken. So this way we have to do. The labels here refer to the drug function. We have considered the 12 drug functions, and these 12 drug functions are referred over here under the heading of output drug function. You can see is here we have the first one is RESP, that is respiratory, reproductory. Then we have others also like the gastro related, CNS, central nervous system related, inflammatory, derma related to the skin, hematology, here, urology, and cardiology. So different types of drug function. Our main task is, let's say I am given this drug structure, drug property, and I have to predict under which type of drug function it is going to fall, so that this can act as a first step to screen out the drugs for the drug repurposing purpose, we can say. So in this actually we have the two major component. The first one is handling the class imbalance, and then another one is training the classifier considering a multi-label behavior, as it has been mentioned over here as multi-label classification. So here it can be seen when I said that data imbalance. Actually, imbalance of if you have a data set and if it is imbalanced, then this is one of the major issue, you can say. Why so? The number of class, the number of, you can say, the labels corresponding to which the number of data instances are quite high, then our models, maybe the ML models or any other classifiers, they used to learn more about those data instances that is coming under that category, and it may ignore, it may not be able to learn the properties of those, you can say, the drugs that are coming under the class label which have the less number of data instances. As it can be seen that under the urology we have just around 73 samples, whereas other two, ANU and CNS, it is around 2000 and 1800. Then we can say while our data is imbalanced, our data is biased, then our classifier may also be biased, because it is going to learn from the biased data, then definitely it is going to perform in a biased way. So this is the observation or the problem that actually we have deal with, and generally we have the SMOT to address the class imbalance. There are a number of methods to deal with it, the class imbalance issue. The one we have picked up is your ML SMOT. ML SMOT stand for multi-label SMOT. That it means it is a adapted or customized, updated version of SMOT that can deal with the multi-label data set. So this one we have done. Actually, very briefly how it works. ML SMOT actually works by considering the number of data instances around its neighborhood, and then it try to, you can say, the generate a kind of similar sample. It is not going to change the attributes, or you can say it used to replicate a any of the data instance, and then it will give, by considering the majority class voting and all those things, different labels. So this way it used to work. More or less, again, in a very concise way, we can say it works based on the nearest neighbor concept. Then we have the issue of the multi-label classification. So for this, I will move to here. Like in case of the application that we are dealing with, it is specified over here. Let's say we have the drug one, then this drug may comes under the different labels, different classes, starting from the drug function 1 to drug function n. Here we have n equal to 12. So if this is the scenario, can we apply a classifier directly to for this purpose? No, we can't do so. So we have to deal with it. Then there are few options or few techniques that we can consider. The first one is your binary relevance. That's like written as BR. Where what does it mean? It means I am consider here X represent the you can say the independent data attributes of instance, and y1 to y4 are your data labels. So what will you do? You will partition that multi-label problem into the binary problems. So earlier you have a problem, a single problem that is multi-label classification, but you transformed it into the multiple binary classification problem. This is the simplest approach, but it never focus over the relationship, the possible relationship between the labels. Then the another approach that can be is your chain classifier, where what we used to do, we generally take the data instance and consider its first any one data label. Then that is one problem. Then considering the earlier data label as its data attribute, we will predict the next data label. So it is forming a kind of chain in between considering a data label as a you can say the class attribute, and then considering it as a independent attribute. But chain classifier is computationally very intensive. Then again, there may be some kind of you can say the dependency or the way we are processing. So we have to do one you can say the random iteration, multiple random iteration we have to do, and it is computationally intensive. The issue is only this, otherwise it is going to capture the any relationship if they're into the multiple labels. In the current work, opposed to it, we preferred binary relevance. Reason being, if one drug can comes under one drug function, then after going through the existing literature, we realize that there is not necessarily going to be any relationship between the multiple labels or the multiple drug functions. Then we thought like it can be a better option, and even we tried both, and the results were quite comparatively better, and also taking less time while we consider the binary relevance. So this way, what we did using the binary relevance, here we have converted our multi-label classification problem into a into multiple. Here we had how many labels? 12. So 12 binary classification problems. This way we did it. Then we use different base classifiers, and these base classifier have been same across all the 12 binary classification problems. First one has been the decision tree. Then we move to the extra-tree classifier, k nearest neighbor. Then we multi-layer perceptron neural network and random forest. So after applying these things, then we analyzed our results in terms of different performance measures. So here precision, true positive rate, and F1 measure. Let's say a brief discussion about these things one by one. The first one is the exact match ratio. What does it mean? It means we have 12 labels. Then we have the information of all those 12 labels corresponding to a data point, a data instance. Then what are the values in the predicted vector by our different classifiers? If there is an exact match between the original vector, original label vector, and the predicted label vector, then we will count over it. Let's say out of 12, it is an exact match over 10. This way. So we have to see like exact match. Similarly, like where it has been predicted 1, then 1, 0, then 0, then how it has been done. But generally termed out to be a little bit harsh performance measure, and you want to have an idea exactly how it has done, then that it is one of the good option. Then we have the precision. uh, Before precision here refers to the, like we can say the total number of detection that have been raised. It means, let's say, how many number of labels have been predicted corresponding to a data instances, and the actual the number of labels corresponding to that data instances. Here it also includes the, you can say the, we have to consider the false alarms. Actually, let's say a data instance comprise only 6 labels, and your method is predicting, or your model is predicting 10. Then we can say total detection or total prediction that have been made by the model is 10, but actually it has been only 6. So it means 6 divided by 10, and this 10 comprises the actual ones plus the false detections also. Then we have the true positive rate. It means, let's say, earlier we included in the denominator factor that false alarms. Here we are not going to include the false alarm. The only difference is this: in the numerator, total number of label predicted that are actual, you can say the correct prediction, divided by the originally how many number of labels have been over there. F1 measure is you can say the harmonic mean of your precision true positive rate, sometimes also termed as your true positive rate as a recall. So while we have to analyze, compare a number of results, then instead of considering a trade-off between the precision and the true positive rate, two different entities, why not to focus on the F1 score? That's why. Then the another representation may be in terms of the ROC AOC curve, and here we have given it for different methods. Here it can be seen that ROC AOC for your MLPNN on SS dataset, and another one is for your ETC, depending upon the model how it is performing. Then here we can say, in terms of ETC, it is better as compared to your MLPN over the smile string dataset. Then this is the overall summarized results that we obtained using this entire architecture. Here we have the model, that is your decision tree, and EMR your other measures, like EMR is the exact match ratio, precision recall, F1 score, ROC, AOC. Then here we can see that we have performed different settings, you can say. That is binary, CC stands for chain classifier. As I mentioned, that we tried both and we obtained the results better in case of your BR. So I have included those results over here. We have the CC, that is your chain classifier, BR binary relevance, and BRMCF is your binary relevance multi-spot classification for drug functions, the proposed one or the one that we have given in the architecture. Then here it can be seen that across, though overall almost all 5 models have performed quite well, but still ETC and RF are better, followed by your MLPNN in most of the scenarios corresponding to the, here it is for your SS dataset. Similarly, it can be seen for the 17 MD dataset also. Right now I am mentioning about the in terms of the models. So ETC, RF, and followed by ML, PNN. But if we have a look over this table and the earlier table, then it can be easily seen that the results are better, far better in terms of your smile string data as opposed to your 17 molecular descriptor. Similarly, moving to the other data sets, this one for your protein sequences, here we have again the in terms of model, almost it is in most of cases extra tree classifier and random forest has performed quite well, and the results on protein sequence data set is comparatively better as opposed to the 17 MD, but for, you can say, a little bit less in terms of performance as compared to SS dataset, that is your smile string representation. Again, we can see that in case of chain classifier, the performance is quite poor. Then the question arises, why so? Even in case of BR also. Then here in case of chain classifier, the reason is this: there has been no relationship between that labels, and we unnecessarily try to impose that thing, and model is a little bit confused, like what to extract, what type of relation, and what to not. In case of BR, actually, the reason may be that the data balancing has been the issue, and it is further compared with DNN, that is deep neural networks. It has been done corresponding to all the data sets, and it can be seen that results for deep neural network architecture is not so good. Why so? Generally, nowadays, deep learning is in trend, but it is not like a written statement or a proved statement that in all application deep learning is going to perform well. No. Whenever you have a problem at hand, then first of all try to see, like, is it really necessary to move to those complex architectures, different deep neural networks, or is it sufficient to deal with the simplified form of the classifiers? Here we have decision tree, KNN, ETC, and then your RF also. And in a number of applications, simple machine learning techniques perform far better as compared to your deep neural network. Another constraint that you have to take is about the data set. As I have mentioned, when we are dealing with the biological data, then the number of samples happen to be low and high, dimensionally happen to be very high. But deep neural networks are data intensive, also the computation intensive, but they require more data to train itself. What about the synthetic data generation? Then it is not a good idea to use the synthetic data generation approach while we are dealing with you can say the biological data or some other kind of application where it deals with the, you can say, the live organisms, because whatever is generated synthetically not necessarily going to mean that that exists in real life. The thing is this: in case of images, we can do some kind of thing and we can generate synthetic data, a good approach. Reason being, let's say a picture has been taken from this angle, then there is a possibility it may have been taken with some other angle. But this type of, you can say, the luxury is not pertaining with the biological data, one thing. Then similarly, we did it for the gene expression data set. And if we overall, you can say, the rank the database base data sets based on their performance, then first of all, it is with the smile string performed the best one, after followed by the gene expression and the protein sequences, and then 17 molecular descriptors. Further, to analyze the results, what we did actually, we visualized a co-occurrence network. What do you mean by a co-occurrence network? Co-occurrence network refers like what is the possibility of the occurrence of two drug labels together. If I am saying, as per my data, that the probability of occurrence of urology and CNS labels is around 70%, then what it signify in real life? It means the drug that is related to urology may have subsequent some significance while we are dealing with the CNS. Though this is just you can say again the synthetic example. I'm not sure about its background, whether any such drug is there or not, but many of them have been over there while we cross checked it with the literature. Then, so by this point of time, is there any query? Is there any query? Okay, let's continue. This was the another study, actually, very briefly, I will mention, to study about the cancer disease, mainly with the, here I will describe it. As I have mentioned, when we are dealing with, let's say, any disease, then our main focus is over how the genes are interacting and how these are responsible for a particular disease. Then here it can be seen. Let's say I have a gene A and another gene T. Then gene A is like any gene, and GT is refers to the target gene. So a number of work have been done over there, that if there is any change in the expression level of gene A, then whether it is going to enhance, it means increase the activeness of target gene, or whether it is going to decrease its expression level. This type of works are there in the literature, but it can be more, you can say, the useful if opposed to it we can identify this thing is termed as your gene pair. So opposed to gene pair, is there any possibility to extract the gene triplets? Then, in terms of gene triplet, we have three gene. You can say the combination of three gene, where gene A is the activator gene, gene T is the target gene, and GR is your repressor gene. What does it mean? It means, what is the role of activator gene? It means whenever there is a gene expression level is high, in case of activator gene, then the expression level of your target gene is also high. Similarly, if the, what about the repressor? It used to suppress the expression level of the target gene. If it is high, then it is going to suppress. If it is low, then it is not going to affect that much over the target gene. So we try to focus over this type of problem, and this is the overall steps that we have followed for this work as well as the earlier work. The code and corresponding data sets, everything has been uploaded over the IEEE, related to the IEEE transactional biology, computational biology and bioinformatics. Then source code is also there that can be downloaded and used if it is required. Then here the first thing is the data collection. Then we refer to the key gene. It means if we have, let's say, 4,000 or 5,000, okay, we will come to it one by one. Then we have a designing a fuzzy system and then generating the gene triplets. Very briefly, we will have an idea of it. This was the data set that we have used. The source code is available. It can be applied to some other data sets also and can be seen like how it is performing. Then it is lung adenocarcinoma, as we dealt with the lung cancer data sets, and it is publicly available. And the GUS session number is your GSE 10072. It comprises 107 samples, out of which 58 tumor samples and 49 non-tumor samples. Here it can be seen easily that the number of gene is to around 22,000 and the number of data sample only 107. I mentioned it earlier that number of sample happen to be very low and the dimensionality happen to be very high. Here the number of gene actually representing the number of dimensions. So what we did, once we had the data, then we normalized it and few processing steps we took. Then the question was, out of this 2200 gene, whether all are important for the lung adenocarcinoma. Actually, no. Then it means we can go with any dimensional reduction process. We can use PCA, we can use some other method also to reduce the number of dimension. But opposed to this, instead of going with the standard this thing, we preferred the approach of rough set theory. Because rough set theory provide an option to find out the reduct. It means you can say the reduced representation in terms of the dimension of a data set. For this, theory can be taken up from any of the book, but the tool that we used, it was your RSCS tool that we have used to find out the reduced version of our data set, not in terms of data sample, in terms of the number of gene. And to our surprise, Well, when we followed this rough set theory process, it is a standard process to find out the reduct, where reduct represent the reduced number of dimension. So I'm not going into those details. Here is the thing. Here it can seen that it has given us 12 different options. Like this can be one reduct, one possible reduced number of dimension. This can be another one. This can be another one. This way it has given us 12. So to be on the, you can say, the safe side, what we did, instead of selecting any one out of this 12, though it was okay to do, but we took a union of all the genes that are there. And as a resultant, we had 53 genes. So even considering all the different representation of the reduced data set in terms of the number of dimension, we just had 53 number of genes. So it can be seen out of 2200, we came to 53, and thanks to rough set theory option that we applied, even the performance has been found to be good. Then once we did it, then what we do, we divided our data set. Here, as it can be seen, here we have the number of tumor sample 58 and number of non-tumor sample as 49. So once we identified the key genes, it means very useful, that are actually going to be useful or responsible toward the lung adenocarcinoma. Then we divided our data set into tumor data set and non-tumor data set, because after this our role is not toward any kind of prediction, it is more toward the gene triplet detection. Then we, using the fuzzy system, we designed a fuzzy system considering our role approach. Like here, high in terms of this fuzzy rules, we can say if activator A gene, activator B, it means refer to the repressor gene. If both are high, then definitely the target gene expression level will be medium. This way we did the prediction, and then we took only top 10% gene triplets out of the total combination that have been generated based on the predicted value and the actual value. That is your RMSC. Root mean square error. We have, based on that, we have worked on. And the total number of gene triplet combination we had, it was 53 permutation considering a combination of 3. So now you can imagine that the number of gene triplets, possible gene triplet combination, have been very large. We strict ourselves just only to top 10%. And based on that thing, we analyze the data. Here it can be seen like these are some of the sample gene triplets. Here FRMD4A, it is representing one gene. SNRK is another gene, and MRPL41 is another gene. So in this case, the RMSE has been 0.0397. Similarly, top 10 has been taken up. Then now question arises, because there is no standard database in case of gene triplets. For gene pairs we have a limited one, but for gene triplets there is nothing. So what to do? Then we did it with the help of, you can say, the existing biological literature without using any tool. That's why we restricted ourselves only to 10%, because it was very difficult to verify all of them. It was actually not possible doing it manually, but we did it for top 10%. And for this, we collected the data about the gene functions, their relationship from NCBI gene database, gene cards, and also some of the interaction from genemania.org. So this way we collected, then we verified like how many of them are actually existing and how many of them matching with our prediction. Then while we consider just the top 2% of the triplets, then actually there have been total 75 gene triplets, known one. Out of that, only 3 were matched. But the slowly we moved to the 10%. Then out of 75, 63 matched. If we had done a comparison with other method, it was quite good. Again, in non-tumor data set, it is out of 75, 64 matched. So it was a kind of, we can say, the in terms of 84 and 85, you will say model performance is not so good. It is actually not the model performance. It is stating that out of 75, 63 or 64 are the same interaction that our model have also identified as the relevant in terms of your lung adenocarcinoma. So somehow we can conclude that the approach has worked fine, and some of the gene triplets that are not verified, they may provide a kind of hint to the medical experts to further explore them, to further understand this type of disease. Then similarly, we performed a comparison with other method that we have the mutual information based model. And these are some of the results. Here it can be seen in the visualized form corresponding to a tumor data that here we have the red color edges show the interaction in terms of the gene interaction that have been proposed, that have been predicted by our model and also validated, the red ones. Yellow ones are those that have been found but their existence we are not sure whether these are really existing, because being from the field of computer science we can't go to the lab and verify these gene interaction. Someone expert in the area of bioinformatics or maybe in the biological sciences, he or she can do that. So it has been left open, entire thing has been uploaded, so it can be taken up further. Similarly, in case of non-tumor data, we have the green ones which are identified as well as validated. Yellow ones that were identified but we are unable to ensure their existence or validate them from any of the existing literature. Then there are the some of the in terms of the unique edge in terms of your tumor. And similarly for your non-tumor data, and these are the common edges. Here it can see like it is a kind of verification that why we divided our data as tumor data and the non-tumor data. Here it can be seen the number of interaction between the gene that comes under tumor data as well as non-tumor data are very few, because it is quite logical. If a gene is expressing heavily in normal condition and because of any environmental reason, maybe because of any reason that has resulted in its decreasing it, suppressing its activity level, and it because of which if that disease is occurring, then that type of information or that type of behavior is not going to exist in the disease case, because high level in normal and let's say suppressed level in case of tumor, or it may be vice versa. So again, it is a kind of verification to the assumption that we took. And these are some kind of hub gene. Hub gene are quite useful while we are dealing with the biological data for mainly with the disease point of view. Reason being, let's say a particular gene is responsible for a disease, and this gene is having its interaction with a number of genes, then it means we have to target multiple genes, maybe multiple. That's why in drugs also we have the different kinds of substances, and that way maybe targeting different you can say the targets. Then is there any hub gene that can control multiple genes? Then why not to target hub gene directly instead of targeting the multiple gene? This kind of literature is there. That's why we observe like whether there is some kind of that information is with our predicted gene triplets, and some of them have been verified. This was a real time kind of interaction. This type of biological literature actually we extracted then with the help of the domain expert, some medical expert. Actually, for us to even it was very difficult to understand some of the medical and the biological terms. But with the help of a medical expert, we did it for around 75, you can say the uh, gene triplets. So about the LLMs, actually nowadays LLM is quite a buzzword. Then from for biological data, what are the option it or what is the scope of use of LLMs? Then few things has been started, but like the BioBert, BioGPT, CDGPT, DNA BERT, and all those things. But many of them are actually dealing with the literature kind of thing, biological literature type of thing, extracting databases automatically, extracting documents from the biological existing biological literature automatically. This type of thing it is performing. But if we consider it from the like the forensic science point of view, biomarker detection, plant modeling, maybe the preventive and precision medicine, then the role is yet not has been that much uncertain. But one possibility is there that definitely LLMs can help us in the way while we have to verify our results and there is no direct tool with the existing literature. Then there is it is going to have a promising role. So with this area can also be further explored. And thank you from my side. Let me wrap up with this with some question if there any, and then we will move to the. So is there any query? Am I audible? Okay, then let's start with the hands-on session. So now moving toward the second part of our session, that is a hands-on session. Let's welcome Miss Anushka, who is working in this area, and she will deal with the hands-on session. So if there is an query, then I am over here and we can move ahead. So Anushka, it's handed over to you. Please go ahead.
Okay. Ma'am, my slide is visible?
Yes, your slides are visible.
Okay. So good evening, everyone. I'm Anushka Chaurasia, a PhD scholar working under Dr. Yogita. So today I will be leading a hands-on session on machine learning models applied to a drug function prediction as well as brain cancer prediction. So in this session, I'll cover various aspects of our data set that will include exploratory data analysis, handling missing values, addressing class imbalance issues in both multi-label dataset as well as multi-class dataset, and training our model on multi-label data. So let's get started with the brain cancer prediction using gene expression data. So in this session, we are basically dealing with the tabular data. So the first one, this one is the brain cancer prediction data set. And the link of this data set is this one. This data set has been extracted from a Kaggle platform. So in this, there are total number of 5 classes, and this problem is a multi-class problem where one sample can belong to only one label. So here these classes represent different types of brain tissue or tumors. So here the first class is appendomoma, which is a type of tumor that arises when the ependymal cell lining with the ventricles of the brain and the central canal of the spinal cord. The second one is glioblastoma, which is also known as GBM, and this one is highly aggressive and malignant type of brain tumor. And the third one is medulloblastoma, which is a type of a cancerous brain tumor that originates from the cerebellum, the part of brain. And the fourth one is the normal, which represent the sample that do not exhibit any kind of tumor characteristics, serving as a baseline or a control group. And the last one is phylocytic astrocoma. This one is also a slow growing and typical benign tumor that arises from the astrocytes, which is a supportive cell in the brain. So in this complete data set, we have a 5 classes, including normal one, and there are total 130 samples. So first, and this total, so this prediction framework is growing through the entire machine learning concept, from data exploration to pre-processing of the model building and the evaluation. And we will focus on using knn, k nearest neighbor classifier, as well as random forest classifier. So first we will see how to import our data set. For that, you need to download this data set from the given link, and then you can either directly upload it from using this icon, or you can upload the dataset directly into a Google Drive, and then you can mount your drive and access by using this read.csv package. So first what we'll do, we will import two libraries. First one is NumPy and the second one is Pandas. So these libraries are essential as we are dealing with the numerical operations, tabular data, which include categorical values as well as various serial combinations. So in that case, we need to import these two libraries, and these deal with numerical operation and data manipulation. So now we have imported these libraries, we have extracted our data set, passed this path here, and here one more point is that we have used index column 0. So we want that our data set will be appear from the starting one, that is from the samples one, to take this into a use that one as an index. Now next we have, you if you want, you can print your complete data set, or you can see only the 5 rows of your data set. So here I have used head column, which will represent only the 5 rows, because only we want to see whether our data set is completely imported or not. That's why we have used it here 5. You can also write it here 1 or whatever you feel. Now next, after loading our data set, we inspect that the first few rows with the head one, and we'll get the statistical summary with the describe, and print the data types of our column. And this is the initially data exploratory analysis works. So here you can see now our data set appears here. Here first one, this type will represent the label. Earlier I have told you we have a 5 label. So now here we have imported only 1 row. That's why here only showing appendio muma. So if I remove this head, we can see our complete data set will be here, including the total number of samples as well as total number of features. Now next we have to check that what is our data type natures, like how many, what is the mean value, what is the standard deviation, what is the minimum value that is included in a particular column. So for that we need this one describe function. So this describe function is used to generate a descriptive statistics for the data frame, and this will provide a summary of central tendency, dispersion, and the shape of our data set distribution. And this will exclude the non-numerical values. It means this will show only the numerical values column. So here when we will run this, you can see only the numerical columns are appearing here, where all the values are numerical, and this type, which is our label, it's not appearing because this is a in character format. So this describe function will not consider this one, it will only consider the numerical data. And the output typically include various types of values, that is count, mean, standard deviation, minimum, maximum, etc. So the first will know what does count mean. So the count will represent the number of non-missing values in the column. So here total 130 samples we have, and there is no missing value because we can cross verify it from here. 130 rows and this count is 130, means there is no missing values. If there is a single missing value, then it will be 129 and so on. Now next one is mean. So this will show the what is the average value of each column. Third one is the standard deviation, which measure the spread of data, how our data set is spread in the complete data set. Third one is the minimum. So this minimum show what is the minimum value in a particular column, and the maximum will show what is the maximum value in a particular column. And here are 3 interesting rows. First one is 25%, 50%, 75%. So these are the quartile, which will show that the value which is below 25%. So the first one is 25%. So here you can say, see this much of data are present below the 25%. Next is 50, where it's written 12. So this much of data is present below the 50%, similar with the 75 one. So this will show the total statistics of your data set, which is very important while you are dealing with the tabular data. Now the third function is to show the data type, like our each column belong our each column belongs to which type of data types. So here you can see the first one is type, which is object, because here it's written it's this is a class label, so that's why it's written in a character one and it's showing the object. But other than the type, all the columns are float 64 data types, and here you can cross verify it. See, everything is in a float format except this one. This is in a object format. Now the next So now next we have to extract our feature as well as our label from the complete data set. For that, here we are using a ialloc function. So as previously I already told you, the first column is our label, and except that all is our features. So here that's why we have written here one. So except one, all are our features. So when you run this code, you will get all these feature in a single variable, that is feature. And the next is, after extracting the feature, now we have to extract the classes. So rest are is the classes, or either you can use the ialloc function to extract the class, or you can just write it here, the column name type unique function to list. So here there is a so here there is a breakdown of each part of this particular cell. So first one is data, in bracket there is a type, so this select the type column from the data frame. So here this is a type column, this is a type column which is our label. So first we are selecting this type column from the data where all the data set has been stored. Now next is dot unique. So this method return an array of unique value from the type column. So there are 5 unique values, and it is returning only the 5 unique values uh, from that type column. And this will effectively remove, if any duplicates value are there, this will effectively remove that one. Now the last one is dot to list. So this will convert all the array into a unique list format. So we can then extract the unique class from a type column, which help us to understand the different categories that is present in our data sets. Since our model required a numerical label, so now we have to convert all these values into a numerical format. Either you can do one hot encoding or anything, but here I have represented it with a numerical values. So the first one here, we have selected the type. Now we have to use a replace function that will replace the particular character into a numerical format. So you can see, if the type column contain a categorical data representing different classes of group, this class will hold a list of distinct categories. So here it's already listing the distinct categories. Now I'm using replace method, and which will replace each and everything, and the result is assigned to the y variable. So this series y now contain a numerical code corresponding to the categorical value in type column, which can be useful for numerical or a machine learning analysis, whether categorical data need to be encoded as a number. So here you can see I have assigned appendoma as 1, glioblastoma as 2, similar normal as 0, and so on. And now I have printed this y1. So this sample corresponding to a label has been printed here. Now next we want to see, everything is done like in our data set, there is no missing values. We have already converted our categorical data into a numerical format. Now we have to see whether our data set is balanced or not, because if we'll run our data set in a non-balanced, like in non-balanced format, then it will definitely give a poor result or sometime a false result. So now we will check whether the samples are balanced or not. So for that we need to use this matplotlib library, which will create a bar chart that visualize the number of samples in each class, and this will help us to check the class imbalance in the data set. So here we are importing the matplotlib.pyplot module, and we name as a plt. Then we are using a class count. Class count is a variable in which we are storing the type and count the value, and this will create a series of class count that contain the count of unique number of values in this data set. Now next we are just plotting using the figure, and here we are writing the total number of sample in each class, and this is representing the X label, this is representing the Y label, and this is the rotation. This is, and now next we're using plot dot show to show the a complete chart. So here you can see there is a huge class imbalance problem. So either you can solve this by using oversampling, or you can do by using undersampling, by removing some of the data, or by using by adding some of the, by doing augmentation, by adding some of the samples. But before doing all these things, first we need to run our model using this original data, like without balancing, because sometimes you, if your model is good enough, then it can capture all these things and give you a proper results. So every time balancing is not important. You first have to check whether your model is giving correct result, test on test as well as on trained data, to clarify whether you want to augment or not. Because if you augment, then it means you are adding some synthetic data to it, which is not which is non-existing data. And if you are deleting some of the data, it means you are removing some important informations that may be important to your model. That's why we will first focus on this original data. So now here we have to normalize our data set, because our data set, see, from data set describe, we have already seen uh, various difference. Mean is 12, mean is also differentiate from 12 to like here 5, 6. Standard deviation is also having numerous values, same with 25%. Maximum value is also different. So this data set is not normalized. There's different values. So this is also a problem. For that we need to use a standard scaler, so that it will normalize our data set into from 0 to 1. Like if your values is 12, then it also will normalize your values from 0 to 1. So here I am using the standard scaler, and obviously I'll apply this thing in my features only, not in the target one, because my target is already in 1 2 3 4 format, and I don't want to like change that one. There's no need, only a need in the feature one. So now I have already used standard scaler here and normalize my features between 0 to 1, and from here I have printed this one scalar. This converted it into data type. See, initially it will be in a numpy in array format, but for better visualization you can convert into a data frame, so that you can see like this. So here see, all the values are converted between 0 to 1 format. Now next you have to describe this one. So when you will describe, you can see almost all these are in a same one. Now next, our data set is prepared. We have done our exploratory data analysis. Now we have to like split our data set for training as well as for testing one. So for that we will use train test split function, and in my data set I am like using an 80 to 20 ratio. Means like 80% will be used for training and 20% will be used for testing one. So this is a crucial for why we are using this, because this is very crucial for training our model. So now we will import. Here our data set is divided, xtrain, xtest. You can print xtrain as well. Oh, it's not running because I haven't run the complete code. Even you can print out the shape of your data set, like using xtrain dot shape function. You can print what's contained in your xtrain as well as what is in your xtest. Now after that we will use machine learning model. As I've already told you, we are going to use KNN as well as random forest. So first for KNN you need to import KNN from this package, like sklearn package. You have to import KNN, then you have to pass it to your neighbor, that it will consider only 5 neighbors, and you can change this parameter, and this parameter always be in a odd number, not in an even number, because sometimes what happen, if you keep it in an even number, then there will be confusion. Now what if for false one is also true and for the true one is also two samples, then the model will confuse which one is to assign. So we always keep it as an odd number, so that it can be easily, the prediction will be easily. So now after importing this package k nearest neighbor, from here we need to fit this in a training sample. So here I am using this variable knn dot fit function where I'll pass x train as well as y train. So in x train there is a features, and in y train there is a labels. Now after you run this, your model is training inside, and here you can change it accordingly, like 5, 3, 7, but mostly we used to keep it as a 5 because in 5 it will give you better results. Now next one is, now your model is trained completely. Now you have to test your model whether it is, whether their prediction is correct or not. So here the X test will be passed, which contain the 20% of your data set, and we will use for prediction dot predict function. So now I'm storing dot predict here, and now predict probability I'm giving X test as 1, and this is a prediction probability what I want. Now after running this, I'll plot my confusion matrix, and then I'll plot my classification report, which will include the accuracy and all those results. So here I am plotting my confusion matrix. So basically, what is the confusion matrix? So the confusion matrix, this is a table which is used to evaluate the performance of the these prediction models, and it will also show that what are the actual values that is predicted correctly and what are the negative values that are predicted negatively. So here see, it's a multi-class problem. So that's why we have a 5 classes. And from this confusion matrix, we can say our model is doing pretty good because it's classifying everything in a right way. So the first one, this will represent the true positive. Like what was the true samples were there and how many samples were correctly predicted. So there were 2 samples and all the 2 samples were correctly predicted. Similar, here is 11. So means 1 and 1 means there, this one class was correctly, there was 11 sample and all the samples were correctly predicted. But when you see here, there is a 4 samples, 2 uh, there is a 7 samples, but all these 7 samples are not correctly predicted. Some of the 2 was correctly predicted, there is a false prediction, and some of them was a false negative, and that was predicted as a true one. So from here you can check whether what was the actual value and what was the predicted results we are getting. Next, see. Next is our classification report, which tell us what is the what was the false positive rate and what was the accuracy of our model. So from here, this classification report is a package that you can import from the matrix. This is a classification report, is a basically function which you can directly import from the matrix package. So here I have already imported. See, from here matrix package I have already imported ROC score, confusion matrix, classification report, and ROC curve. So I am directly using that particular function here. And here I am passing the original Y test and what was the predicted result. So first one is the precision. So this will indicate the positive identification that were actually correct. So means see, from confusion matrix, I've already told you there were only 2 samples and all are correct predicted. So that's why here it's 1. 1 means 100% result we are getting, and also recall is 100 and upon score is also 100. So recall is actually a positive, actual positive. What was the actually positive results and was correctly classified. And in sense you can say it's a true positive rate, and the FN score is the harmonic mean of these two, and precision as well as recall. Now the second one, in one you can see this one is showing as 11, and here the precision is quite low, and but this one recall is quite high. Similar with the second one, in second label the precision is quite high, but you can see the true positive rate is very low. It means it would the positive identification of the proportion is actually correct, but the true label that was actually true was not correctly classified. Some of the true label was classified as a false. That's why here the recall is 0. Similarly, you can analyze all these matrices, and here you can see the accuracy. The accuracy is 81, means our model is classifying 80%, 81% correct results. Now here to I have used KNN. Similarly, now we can use the random forest, and this is the same pattern. Like you can import the random forest classifier using the ensemble package. So there are different packages inside the sklearn library which you have to call for a distinct machine learning models, and all the pattern will be same. Only here you need to import different algorithms. See here I have imported random forest classification classifier, and now I'm storing this package into a this function into a particular variable, doing the same thing using dot fit function, and passing train as well as x train as well as y train function here to get the to train my model. And after training I'll call the same thing, same model, to predict our y test, which is unseen data set. So first I'll train my model using the seen data set, then I'll check on an unseen data set, and I'm using the same code, r.predict, like passing my model here for prediction of probability, like that. Now I'll just plot my confusion matrix. So see, here is the confusion matrix. Here this true one is giving pretty good results. Earlier it was showing bad one in KNN. See here 222, but here it's showing pretty good results. Now you have to check on the classification report, because we can't rely only on the confusion matrix or accuracy. We need to cross verify our result using distinct matrices. So now here you can say all are giving the almost good result, but in 4 we are getting 0 0, as here is only one sample, and it's giving that that is wrong. So we are getting 0 0 in all this one, and here the accuracy is 96. So in this accuracy has increased, but the problem is the fourth one is not identifying is as a correct, which was in KNN. So if this thing is there, then we will definitely go with the KNN, because it's actually identifying all the labels and giving the results at all the labels, unlike this one. I think this one is showing underfitting or overfitting issues. So this was all about the multi-class classification. Do you have any doubt regarding this? Because now we are going to move into multi-label one. Anybody have doubt regarding this? Okay, now we will go into the multi-label one. Multi-label classification. So multi-label classification it means that one sample will belong to multiple label, and this we will do by using the drug function prediction using gene expression. Here also we are going to deal with the tabular data. So from this one, this is the similar same. You have to use pandas and numpy, because you are dealing with this tabular data. You have to use this one for analyzing your data set. Now here I am just importing my data set. I've run the results. So here you can see there are several columns, total nine columns. So here these are all the gene expression, but when you go with this drug function, these all are drug function. There are 12 drug functions here. So here you can see these are the samples. Now these are samples. Now these samples can belongs to more than one. See here, this also belongs to one. If you can see this third one here, it belongs to cardio as well as respiratory system. So this is a multi-label classification problem, where one sample can belongs at one time, one sample can belong to multiple labels. So now here we have to solve this, and this can't be solved directly by applying KNN or random forest. For that we need one more function that can bind these together. So here first we'll drop the first column, because this is the ID, and we don't need ID while training. We only need features as well as target variables. So we will replace this first column. Then we'll print our data shape using dot shape function. So here there are total 959 rows samples and 990 columns, including target variable. Till now we haven't bifurcated our dataset into feature as well as into labels. Now we'll check the missing values. So here you can see there is no missing values. Same will go with the data description. We'll describe our dataset, as there are 990 columns. There are more than, you can see here. And here the minimum values of label is 0 and maximum is 1. There is nothing between, that's why these things are 0. Now next we have to divide our data set into features as well as column, features as well as label. So here there are 978 gene expressions. So these 978 are all features. So here we are passing all the features into X. Now next, other than 978 are all my target variables. So see, these all are targets. This 12 one is target one. Now next we have to plot to check whether this data set is balanced or not. So here if you plot, you can see this data set is not balanced, as well as in the first, this one, anti-infective, there is no samples that belong to anti-infective. So you can remove this samples, remove this target variable, because there's nothing, no samples that belongs, so there's no need of taking this one. Now we have seen here there is a class imbalance issue, but the problem is this is not a normal class imbalance issue, because it's not a binary classification problem or a multi-class classification problem. Here, though, one sample can belong to multiple class at the same time. So to solve that, we can't remove this class imbalance completely. Like if we include 100 sample here or 300 sample here, it can't be balanced. Like, so for that, there is some special matrices that you have to check. So first, that you have to check what is the mean class imbalance ratio. Means here, so here you have to check the mean class imbalance ratio. So here you can see, when you will run this code, you see how many class count, class 0 count, and what are the class 1 count. So here in anti-infective is showing 959, because there is no sample. It means by default it's taking as a 0. See, here is 0, that's why it's showing 959, and total, so we have 959 columns, 959 samples, that's why there is no one. So this is, we can't, we have to remove that one. Next one, there are 892 samples that belongs to class 0, and there are only 67 samples that belongs to class 1. And here is the imbalance ratio is 13.31. Likely you can say there is huge class imbalance ratio in our data set. So now we have to balance this, and there is different thing that you have to check. Here, so I have checked class imbalance, mean class imbalance ratio means per class I am checking, but we can check the complete imbalance ratio. So that, so you can check using the mean IR, like total how many, what is the average of this class imbalance. So here the average is 99, and CVR is the coefficient of variation of imbalance ratio, like what is the standard deviation variation in balance ratio, that is 16. So now we have to remove this one, we have to reduce that this. See, here is the definition of coefficient variation, which will calculate the ratio of standard deviation to the mean of class frequency. And when this is applied to an imbalanced data set, it measures how much the sample size of the class vary relative to the average class size by using this particular formula. And so now here you don't have to balance the data set, you only have to reduce the mean IR as well as the CVIR ratio. So now for that, there is one algorithm, oversampling algorithm, that is ML-SMOD, and the full form of this ML-SMOD is to so the full form is multi-label synthetic data generation. So this technique is used to balance the data set where each example might belong to more than one class multi-label, or in simple term we can say that it can create new synthetic examples for the minority or underrepresented label combination by interpolating between existing samples, and this helps ensure that all labels have enough examples, which can improve the performance of machine learning model on a imbalanced multi-label problem. So what it will do, here are three functions. The first function is this one, the get label function, and by default ML is not use KNN for generating the new samples. So the first one is the get tail label. So this function takes a data frame and a list of quantiles q1 as an input, and it is designed to find the underrepresented, means the minority targets in the data frame, and which are defined as a target that are observed less frequently than a median occurrent. And next one is the quantiles, which next you see there is a quantile, which is an order list value that divide the probability distribution into the equally probable intervals. Now, next is the we have to sum the data frame, and this function will start the summing the data frame along axis 0. Now here is the now here's the get the minority samples. Now from here you have to like this function is this function will identify the what are the underrepresented target. Here you need to give your complete data frame feature one, and here you have to give the target one. You can change the quartile as per the requirement, but the thing is we have already like in literature is already taken 0.05, but you can experiment it according to your data set. Now once you find a minority label, then you have to pass it to this function, this getTel function, with the target data frame y and the quantile list ql to identify the minority label. And this function then select the samples from y that have least one minority label and set to 1. And this indices of these samples are stored in an index. And using these indices, the corresponding feature vector and the target vector from y are selected to the form of minority feature data frame. So basically, ML Smooth, what they are doing, they are just capturing this minority samples, and then they will check how to generate this minority how to generate synthetic data for this minority sample. And for that they are using the k nearest neighbor. As you can see here, I am passing k nearest neighbor, and they will just cross check if the first one belongs to the two or three neighbors, then they will generate a similar kind of data that will belong to same two or three neighbors. So likewise they generate the similar kinds of data set. And this is the complete code of ML Smooth. Here I'm passing, and now here I am generating 10,472 labels. You can reduce this accordingly, but my main reason of using this sample is to reduce the mean IR and CBI ratio. So that's why I'm using this one. So when you run the code, you will get the synthetic data, and after that I am concatenating the synthetic data with the original one. This was my original data set, and this was my synthetic. So using concatenating function, I am just merging this one. And now after that I'll calculate what was my mean class imbalance ratio, as well as what are my CVIR ratio after augmentation. So here you can see after augmentation I am getting 6.45 and 8.70, means this is less than this one, the original, means my data set is somehow not that much imbalance. So now after that you use the data set, and these are the my augmented data set, and see it's the in similar format. For target one is giving 0101, and for this one it's giving same pattern. And after that now our data set is ready, it's already augmented. Now we have to train our model. So for training our model, we can't directly pass this into any model, we need to use some function. And there are some distinct matrices that are used while doing the multi-label classification. One is the this is the accuracy function, and the second one is the Hamming loss. Here the classification report is the same, ROC score is the same, precision, recall, everything is the same, but main thing is the Hamming loss. What is the loss of the particular uh, model we consider here, as well as this is the accuracy function. It means what was the exact value, what was the exact in simple term you can say exact match ratio. Like if the value is 111, and whether the our model is predicting it as a 111 or not, that is exact match ratio that we check in multi-label classification. So for that we have to use one function that is known as binary relevance function in machine learning to get the results. So here binary relevance function means it will take multiple label as a single label. See what it will do, it will just take this as a single label, then in second term this will take as a this is as a single label, likewise it will do. So that's why we use binary Levin's function, and this is a complete code of binary Levin's function. Either you can directly import or you can just write this function. So here I have written this function from this scratch. This will predict the probability, and this for model here you have to pass the model, and this will all the predicted to the numpy. And after writing this particular function, the binary Levin's classifier, you will now write the same. You will split your data set into train and test that we did previously, and then you have to use here decision tree. So here I'm not passing decision tree directly. I'm using that binary Levin's function. So when you write decision tree inside this function, this tree will go here, base estimator, and likewise it will process one by one for C for every class label. It will do recheck base model, it will fit the model, it will calculate the probability, and it will store the result. And after that we have to predict, and for prediction I'm using the same function, that is dot predict function. And instead of printing accuracy, I'm using my function that is main accuracy score, that is exact match ratio. So here you can see the exact match ratio is 98, means my model is predicting 98%. And when you see the Hamming loss, the loss is 0.12, means this model is pretty good working by using the decision tree. And this is the classification report. Here it's 0 because I haven't removed the first column. So if you run this one, just remove the first column. But from here you can see now, if it's giving everything is correct, it means my model is doing pretty well, because it's not taking this one, and else every results are correct. Now next you have to plot the ROC curve. So here I have plotted the ROC curve. This is a function of ROC curve, where you have to pass your y test into numpy format, because it can't take data frame. So you have to convert it into array. Then you have to define a variable, false positive ratio, true positive ratio, ROC score. Then you have to use this ROC curve function, where you have to pass this one and your original y prediction, and then it will compute the micro and micro averages of all these things, and then it will plot the ROC curve, this one. And next I have plotted the ROC curve of each of my label. This one was the overall, what is the overall ROC curve, and this one was the ROC curve of each label, because here we are using binary Levin's function, and it consider each and every label separately, and then it merge it that time. So that's why here we are showing each labels. So here you can see the values are more than 95%. So we can say that decision tree is working pretty good in this data set. Do you have any confusion in this? Am I audible? Do you have any confusion in this file? Okay, then now we will move to the next one, that is the chemical.
Yes, you are audible, ma'am.
Okay, now we'll move to the next one. Earlier we have discussed about gene expressions, that is biological. Now we will move to the chemical properties. So in chemical there are distinct types of properties, string, fingerprints, molecular properties, but here we have considered the fingerprints. So as you can see, earlier our data set is in two format. Now one is the continuous values and one is the categorical values, but now here is the problem. Here my data set is all in a categorical format. So you can see all the values are in 0 and 1 format. There is no continuous values. So now you have to deal with this problem. So here the process is almost same. First you have to remove this pubchem id, because this is a id and we don't use this one. Now after removing, you can see the data set. There are 759 rows as well as 1036 columns. So here is more number of samples compared to the previous one. But all the data set is in 0 and 1 format. This is the shape of our data set. Then we use the data is null, data dot is null function to check whether there is missing values or not. And this too you can also check from the dot describe function. See, from dot describe function, you can also check whether there is missing values or not. Similar thing here, there is minimum is 0, maximum is 1. Income whole data set, same thing. Minimum is 0, maximum is 1. There is no values that is below 25%, 50% or 75%. So now you have to split your data set into features as well as targets. So I'm using the same .ilc function to split my data set into features and format. So here we are using 1024. It's ECFP4 modern fingerprints that here we are using. It will represent the bonds, because the chemical property is basically represented in a like chemical formula. So here each of this column represent a particular, either the bond, either the it's a carbon or it's a nitrogen, or there's a single bond or there's a double bond. So these kind of things is represented, and zero ones mean whether this is present or not, only yes or no. And next, this is our data set. Here again, I'm using drug function, only the properties has been changed. Earlier it was gene, now it is chemical. Now next we will plot same thing to check class is balanced or not. So here earlier there were no samples in anti-infective, this target, but now so there is samples, but this is heavily class imbalance. You can see in some of them there is so many samples, but in some of them there is a very less sample. Like in this one, urological, respiratory, there is very low samples. Now next, imbalance is there, so you have to use ml smooth to handle the class imbalance problem. Same thing, I'm using ml smooth to handle my class imbalance. Here I'm using what is the, whether the data set is this is class imbalance, mean this is the ratio of class imbalance, showing this much of classes imbalance. Here so I have printed for all the data set, for all the features, all the data set, but generally we used to print for only for the this label one. See, this is a maximum 80%. Now next, this one, this is the same. See here what I have did now, I have divided this one, this ml smooth code in this biological one. I have run all in a complete cell, but now here I have divided to show you what is the result after each line. So here I am printing this one, what we are getting after each line. So here we are passing the complete features. See, one by one I am running what is going on after each and every line of this code. What is the maximum class imbalance ratio, then what is the mean divided by this one we are getting here, then what is the threshold we are using. These are the tail labels where the class is highly imbalanced. Now here we are getting the minority sample. Similar, I'm running what are the minority. So here you can see from the tail, this one, from this code, this from this get tail label, you get this one. Like uh, these 5 targets are minority. There is less sample in this 4, so we have to focus on this 5, and we have to augment only these 5 data set to get the minimum class imbalance ratio as well as CVIR ratio. So you can use the same code that's calculating of class imbalance as well as CVIR from the biological one. See, one by one same thing is. Now I am using the k nearest label, then using the MLS mode to augment it, this function MLS mode function to augment. And again I'm using the same 10472 samples, and this is what I got the result. But here you can see there is a problem now. Earlier it was like whatever you are giving, you are getting the similar kind of augmented sample. See, here you are getting 101010, that was expected, and here you are getting all in this normalized format. But the problem is here is in chemical one, because our all the data set was in the form of 0 and 1, and we haven't normalized anything because there's no need of normalizing. But here you can see the samples are, we are getting the distinct samples like 1 minus, in some case 1.0. 1.0 is so fine, you can convert it directly into 1, but in some cases you are getting 1.32, 1.4, so it's not giving the correct result. It means we can say MLS mode is not working correctly in this type of data set where there is only categorical data. Similarly, you can see here minus, yeah, this one is the complete and this one is, you're getting the same thing. And augmentation, so it's giving the correct one in this target one. Similar for multi-level classification, you have to use exact match ratio, this code, because normal accuracy will not work here. This is a similar code. Then again I have used binary relevance, because it's multi-label. I can't directly pass my random forest or extra classifier directly into this data set. I need some of the functions so that it can translate the multi-label into multi-class to do this work. Then here I am using same train test split function for dividing my dataset into train and test, then passing my random forest classifier into this one binary labels. You can use this, you can change this parameter accordingly. Then predict function, and here I'm getting 98% results. Although my dataset is not correctly augmented, but still I'm getting 98% of this one. And Hamming loss is also less, and it's giving this one. This precision recall F1 score, all are we are getting the almost good results. Now, similar, I have used this ROC code to plot ROC curve for a complete dataset as well as for the each and every target variable. So this is all about the chemical one, biological, means multi-label as well as multi-class classification problem. So do you have any query regarding this or any confusion? Am I audible? Do you have any query regarding this?
No, ma'am. Thank you.
Okay, then thank you.
Thank you, ma'am.
Hello, is there any query? Hello.
Ma'am, you are audible.
Okay. Then, Anushka, is there any query from the participant side?
No, ma'am.
Okay, let's wait. Then, let's wait for organizers for some time.
Okay, ma'am.
ठीक है सर. Hello everyone. So I think there is no further queries. So let's wrap up with this session, and the next session will start at 5:50. So you are
15,
free to
15.
break for next 20 minutes and come back at 5:50. Thank you. Thank you, Anushka,
Oh,
and thank you all.
okay. Thank you very
Thank you,
much,
ma'am.
madam.
Thank you, sir. Thank you, ma'am.
Okay, thank you, ma'am. Thank you.
Thank you.
Good evening, participants. I will start the lecture within 5 minutes. Please wait. So I hope my screen. Wait. I hope my screen is visible to all of you. Are you getting my voice? Anybody?
Yes, sir. We are getting your voice. We can hear you.
So participate. Are you getting my voice? Can anyone confirm me?
Yes, sir, we are here.
Yes, sir. Yes, sir, we can hear you.
Okay, 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 okay. So I think my screen is visible to all of you. So today I'm Dr. Sushil Kumar from NIT Kurukshetra, and I will discuss a topic here. The very known algorithms are there. Meta heuristics techniques is there. Meta heuristics algorithm. So the agenda for today, it will be like this. So we will discuss about AI first. What is the AI and how it will work? Then we will discuss one algorithm for this AI part. Okay, searching algorithm is there. We'll discuss that algorithm in detail. Okay, so we will discuss the benefits, the advantages, the disadvantages, everything we will discuss here about this algorithm. Okay, and then because of these advantages, the algorithms are not in use actually. Why these algorithms are not in use? Then we will discuss another technique that is called heuristic search. Okay, to solve the problems, means to solve the complex problems. And then again here also we will discuss the advantages and the disadvantages of this algorithm, these algorithms actually. Okay, and again to remove the disadvantages, we will discuss the techniques used to remove this problem related to heuristic search. Okay, and in meta heuristic there are so many algorithms are there, but here we will discuss only one algorithm. Okay, so we will discuss only one algorithm, that is differential evolution. So many are available. After that you can search it or another, and then in differential evolution I will discuss some application part of this algorithm. Okay, where we can use actually so these algorithm. So this is the agenda for today's talk. So first let me discuss about the intelligence, because this these days we are trying to discuss about AI. So first I want to discuss about the intelligence. After that we will discuss the AI part. Okay. So what is the intelligence? Suppose I ask you this question, as a human being, what is the intelligence? So some general answers will be like this: we have the ability, as a human being, we have the ability to take the decisions. To take the decisions. We can take the decisions. Okay. And decisions, when you are taking the decision, it is not like that you are always, it will give the wisdom. Okay. Sometime if any person is there which is not good in taking the decision, it may be like, or he may be like a fool also. But ultimately this is the power actually we have, we can take the decisions. Okay, decisions, how we are taking the decision, that is a different question. But the ability, because we are taking the decisions, that will prove you that you are a intelligent person or you are doing some foolish thing in your life. Okay, but decisions are important here. Okay, so taking decisions is also not like very easy task actually. How you will take the decisions? Suppose one student came to you and he has cleared the 12th exam, okay, and he's asking you what I need to do. So there are so many options are available. Okay, then you have science background also is there, then we have art side is also there, then we have commerce is also there, and many more are there actually, and medical is there, and all. So many options are available. Even here also we have lot of options are there. CSC is there, EC is there, and many more branches are there. So when a student is coming to you and is asking you which is better for me, then how you will take this decision? You will take some information. Okay, it is available in your brain, or you will ask from your friend. You will take the information about this one. You will take the information about this one, or you will take information about this one. And then on the basis of the data, okay, or the knowledge you have as a faculty, you can take the decision. This is good, or this is good, or this mechanical is good, or triple is good, or BSc is good, or art is good, or which subject is good for future. The decision will be taken on the basis of some data is there, and that according to that, even not data actually. Data is one thing. You need to have some knowledge also. Okay, this is the direct decision you can take. Some another decision may be like that. Suppose a one hot road is there in front of you, so you know very well we can't touch this hot road. Why? Because you have the experience from your childhood, or from someone else, from your friend, from your parents. Somehow you have that knowledge in your brain. That's why you are taking the decision. Okay, don't touch it. So exactly what we are using here to take the decision, we are using knowledge, use of knowledge. We are using knowledge here, okay, to make the decisions as a human being. Okay, so we have some knowledge, and according to that knowledge, we are taking the decision. Sometime it may be data, sometime it may be the past experiences, sometime it may be the experiences from your friends or from your circle. But on the basis of that, you are taking the decision. And decision is not like that we are taking in daily life. Okay. Third ability we have as a human being, ability to generalize. Ability to generalize. What is the meaning actually here? The meaning is we can generalize the problem. Suppose I ask you 1 plus 2, you can answer very easily. Suppose I ask you 1 plus 2 plus 3, again you can answer it. Suppose I ask you 1 plus 2 plus 3 plus 4 plus 6, and like that, plus 7 plus 8, and continue, plus 10, and then you will give the answer 55. Okay. So suppose I ask you, you will feel the difficulty here also, but still suppose I ask you 1 plus 2 plus 3 till 100, then literally you will feel the difficulty in this one. So what human being can do? We have a general formula. So if n, whatever the value, and you want in the sum of these n natural numbers, you can calculate directly from this formula. So this is the power actually we have. So, as a human being, we can generalize the problems. We can generalize the problem. Okay, and it will give the proper solution for all the problems. It is not related to only one problem. So, that is also a power as a human being we have. Another power, we have ability to learn. Ability to learn. So, this is actually ability to learn means from our birth From our birth till our death, we are learning daily. Okay, it doesn't matter what is your age or what is the factor, but we are learning continuously. Okay, it doesn't matter you are studying or whatever you are doing, you are in a business or you are doing whatever in your life, but still we are learning. Okay, and we want to replicate this one in machines. Okay, we want to replicate each and everything in machines. We want to replicate this taking the power of decisions in our machines. Okay, we want to replicate this knowledge. Okay, knowledge based solutions. We want to replicate to generalize the problems somehow. Okay, so your system can generalize. We want to replicate this learning process that is you know very well. We have so many models of related to machine learning. So step by step, in starting, we are taking the decision, then we are using knowledge, then we generalize, and then we are starting learning. Okay, then concept came like machine learning, deep learning, and each and everything. So all the part is of AI actually. All the part of like we are giving the training as a human being, like our brain is trained from childhood to in entire life. So that we want to. Then one more ability as a human being, we have ability to speak, and that is also we are trying to replicate. If you can check, you know very well. So many AI related applications are there which are able to speak. Okay, so these are the some basic answers actually. So for human being, what is the intelligence actually? So these are some. Here we are not considering this emotional part, only we are considering the part which is very related uh, to solve the problems. Okay, so what exactly we are doing in AI then? So these are the answers. So what exactly we are doing in AI? So in AI we have, suppose this is the AI here. Okay, what it will do exactly? So through AI we want to solve the problems. Okay, so we want to solve the problems. So it's a bigger picture actually, and great machine learning is just a part of this one. So how you will solve the problem? Can anybody can answer this question? How you can solve the problems? If you have any problem, how you can solve? So problem solution already we have discussed in last. So you need to take the decision. Exactly we are doing in our daily life as a human being. So you need to take the decision. And how you will take the decision? You have two options in front of you. Because here you don't have a brain actually. Because as a human life, in a human life we have a brain. Hello? Any question? So we have two options here. One is like knowledge based. Some data will be there with you, and on the basis of that, you can take the decision because it is not a human brain here. We are working with machines. Second is search. So searching means namaste. Hmm. So this is like search based is there. So in search based, actually, what exactly is there? We have a presentation in some domain related to work, okay, and then we are trying to find out the solution in particular domain. So find out the, actually you may be doubtful here how the solution is there. So I will give the example, and then you will be very clear that how it is possible that solution is given, okay, in domain. So in domain the solution is there, it means so many values will be there, but solution is also there, you need to search. Okay, in knowledge based, here what you will do, trying to exploit the knowledge. Okay, trying to exploit the knowledge here, exploit the knowledge. Okay, in knowledge based, again some problem may be there, how you have the knowledge. So knowledge may be like you have some memory, and in that memory you have lot of data is there. Otherwise, second is rule based. So if you are from computer science background, you can understand this rule based actually. Like if else, so many rules may be there, and through that you can solve the problem. So this is like a brief introduction of AI, how it is working. So today here we will discuss this part, actually search. I will discuss this search part in detail, okay, and then we will discuss how it is difficult to work with search algorithm, okay, and then we will discuss this another knowledge based also, okay. So let me discuss one algorithm in searching. So we have an algorithm, actually I think you didn't heard the name of this algorithm, that is called state space search. So we are using this algorithm actually to solve so many problems we are solving. Okay, but the name is not that much famous. So exactly what we are doing here, we have a starting state S. Okay, and we have a goal state here. So how I have a goal state, actually this is the solution. We know the solution. How we know the solution? So if you have seen a mobile app is there, okay, in that mobile app some blocks are there related to one image, like 1 5 8 9, okay, 7 5 or 6, okay, 9 or the 3 and 2, and then you need to find out the solution. It will give the solution like this. So 1 2 3, 1 is blank here, so you can move 5 here, you can move 8 here, and like that. So you can imagine one image related app is there, okay. So when you will merge the images at its proper places, then it will say yes, you have done this part, this game you have done, and these are the number of moves you have done for this app. So in this is the one example. Second is Rubik cube is there. In Rubik cube you know the solution. Okay, so one merging state will be given to you. They will merge it randomly, and then they will provide you. And then you need to find out the all the red at one side, green at one side, yellow at one side, white at one side, like that. In that case, also we know the solution. So that is the goal state here. Actually, so many problems are there in which we know the solution. Okay, so from here we have a function. That function will find out the neighboring state here. Neighboring state, okay. So n1 and neighboring state n2, like that. So what exactly you will do here, you will check if n is equal to g. If this is not the case, means here we have a function, actually move function is there, okay, and that move function you will pass this s starting state, and it will give you n or n1, whatever, okay. Again you will pass this move, and if possibility is there, it will give n1, it will give n2, and every time you will match with this n1 is equal to g, the goal state, or n2 is equal to g, Okay, if it is not there, this case is false, this case is false, this case is false. Then again, what you will do? Again, you will use this move function. So it will give you n11. Okay, again it will give you n12. Here also it will give you n111 or another state. And similarly here, it will also give another state. Suppose there is no solution, again you will, with the help of this move function, again you will design the searching. Okay, and again more states will be there. So like that you will move. Okay, so at the end you will shrink like this towards your solution. If your solution is available in the domain given to you, then definitely it will give the solution to you. Means this state space search will take the guarantee. Okay, it will take the guarantee if the solution is there. So 100% guarantee is there that it will give the solution to you. So that much powerful algorithm is actually this one, and it is very simple also. Sometimes actually the name of this algorithm is simple search. Simple search. So that one is simple but very powerful technique actually. So here also, if you want to write the nomination, the nomenclature S is set of states. G is the goal state. GOAL, goal state. Okay, and we have a move function also here. Move function is also required, so which will give you a neighbor state. Okay, so we have a move function that will provide you the neighbor state. Okay, so this is a state space search. So if you want to write the pseudocode, you can write the pseudocode for this algorithm. So it will be like this. So you have an open domain. Okay, in that open domain you will start from the starting state. Okay, and you will check that while this goal state is there, okay, with S. First also you will try. If it is not is equal to true, then what you will do? You will remove it. So remove n from open. Okay, from open, because this is not required. Okay, and then what you will do? Again, open will be with this open is there, and you will merge all the another states from neighboring state. So this is the very simple code actually, or the pseudo code for this algorithm. Okay, for simple search. So let me give an example. So for simple search, actually we are using in our so many problems we are solving with the help of simple search. So I suppose I have a board here which is containing some values. Okay, so I have some values here like 1, 2, 3, 4, 6, 8, 5, and 7. Okay, and this is my starting state S, and I have a goal state here G. So what is my goal state actually? This is the goal state here. So this is the goal state here. So in goal state, it is defined that I want a pattern like this: 1, 2, 3, 8, 4, okay, 7, 6, 5. So this is my goal state here. So here we are using this tag. So we have this blank space here, and at a time only one move is allowed. You can move. Okay. So what will be the possibility here? So suppose you want to work on this one. So you can move this one here. Okay, this one here. So what will be the output? So that is very easy to write the output here. So your board will be like this: 1, 2, 3, 4, 6, 8, 5, and 7. So this is the board here. Okay, and again, suppose you want to, this is not the correct solution, you can match it. But here also, again, one more possibility is there. So what is that possibility? So you can move another value. Okay, so 8 you can move. So I have 1, 2, 3, 8, 4, 6, 5, 7. Okay, and this is also not a correct solution, but again you have another possibility from here. So what is that possibility? So this is the another possibility here. So you can draw this one. Okay, so you can, what you can do, you can move 4. So it will give you 1, 2, 3, 4, 6, and 8, 5, 7. Okay, now you don't have any possibility here in this case, actually. Only 3 move you can do. So this is like n, this is n1, this is n2. So now you can pass this n in this move function again, move n. So this is the state now. Again, you will start from here and you will find out some states like 1, 2, you can move here. From here also, you can move, or 2 states maybe there. From here also, you can move. So like that it will work actually. This algorithm will work. So definitely it will give the solution. Only the problem is here, how many steps is required. So that is also one counter you will use. So how many steps are required, that is the only issue here. Otherwise definitely it will, a solution is there, it will provide the solution to you. So how this algorithm is working, if you will see, so this is the starting state and it is growing like this. Again from here it will grow like this. Okay, from here again it will grow like this, and it is growing in this manner. Okay, and similarly it will grow in this fashion. Okay, more growth may be there, but suppose here you have a goal state, then situation will be like this. After some time it will converge towards the solution. Okay, it will converge towards the solution. So here at this place the growth is exponential. Exponential growth means here you have 2, here you have 4, here you have more means n square, and like that it will grow. And after that you will got the solution in this state space search algorithm. Okay, and this is the problem here actually. When we are saying exponential growth means the time complexity will be very high. So what is the meaning of time complexity? The CPU is there in our system, and for the CPU we are trying to provide an algorithm so that you can solve the problem on time. Okay, it is not like that you have designed an algorithm which is taking more time and it is very difficult to solve with your CPU. So we have so time complexity is a big issue here. Okay, and it is not a simple thing actually, it is a very big issue in this algorithm. So suppose we have a Rubik cube. So I will give you an example to prove that how much difficult actually to solve this problem. So suppose we have a Rubik cube. I think you know the Rubik cube is there. So the Rubik cube, actually it is there. So this is the what we have done till now. So I told you that intelligence, use of knowledge to make decisions, ability to generalize, ability to learn. So this part also we have discussed actually. State space search, then this like set of states, goal state, and this is the example I told you. So here this is the function actually. At a time only one move is allowed for achieving the desired output. Starting state provide only neighboring states, not the goal state. So these neighboring state will help in achieving the goal state. So this is the Rubik cube actually. I think everybody can know about this. What is a Rubik cube? Okay, and if I will merge it randomly, and then you need to solve this problem. Okay, so suppose you have a Rubik cube and you want to solve with the help of computer program, or you have designed this through simple search technique you want to solve. How much time it will take? So when we are talking about time complexity, we are talking about the worst case analysis. Means we are thinking here that the problem will be the solution is available at the last step. Means whatever how many branches are there, how many states are there, all we need to exploit, and after that we will got the solution. So it is not like always true, it may be in between also, but in computer science we will take worst case. So how many phases are there in Rubik cube? 6 phases are there. Okay, and 6 into 3, so like 18 branches will be there. And at a time a user have 20 moves actually. It means these many options are available. A user can move the boxes in 20 different manners. Okay, so that many faces are available and 20 moves are there, then how many states will be there to solve? So 18 is the power 20. And what it will give you? So the states you have 127 into 10 is the power 25 states are there. So that many states will be there. Means the branches. So whatever I am discussing here, that many branches. So you have that many states to solve in Rubik cube. And here I am considering all the states I need to exploit, and then I will find out my solution. So I will ignore this 128 here, and I will consider only 10 is to power 25 states I have to solve. Okay, and I have a system. I have a computer which can solve billion states, million states, sorry, which can solve million state in a second. Yes, any doubt is there? Okay. So, which can solve million state in a second. Million. I have a powerful enough system. What is the meaning here? It can solve 10 is to power 6 states in 1 second. So, what is the meaning here? The meaning here is to solve 10 is to power 25 states, how much seconds are required? So, we need 10 is to power 19 seconds to solve this problem. Okay, it is looking very nice time. So I will take one assumption here. Assume that we have 100 second in 1 minute. Okay, in 1 minute. Then how many minutes are required? 10 is to power 17 minutes. Okay. Still it may be like this. Okay, what is the issue here? Okay. So I will take one more assumption here. Assume that we have 100 minute in 1 hour. Sorry, in 1 hour. Yes, correct. So how much hours are required? 10 is to the power 15 hours are required. Okay. One more assumption, because 10 is to the power 15 hours also you can think, okay, let it be, no problem. Suppose you have 100 hours in a day. Okay, you have 100 hours in a day, and how many days are required? 10 is to the power 13 days are required to solve this problem. Last assumption, I will assume that I have 1000 days in a year. And how many years are required? 10 is to the power 10 years to solve this problem with the help of simple search algorithm. And that is the reason actually you didn't heard about this algorithm. This algorithm is a very basic algorithm and available in literature from so much too much long time it is available, but still we didn't heard, because what is the meaning of any algorithm which is taking 40 billion centuries? So if you want to solve the problem, you will not be there available after to check the solution. Okay, so 40 billion centuries are required, and what is the meaning? There is no meaning to use this algorithm. Okay, and that's why we don't use this algorithm. So this is all about the state space search. Okay, the advantage of this algorithm is it can solve, if solution is available, 100% guarantee it will take to solve the problem. Disadvantage is available in front of you. Okay, sometimes it is impossible to get the solution with this search technique actually. So what the researcher will do? So they can't leave the AI part. So what they do? They come to another algorithm. They have designed another algorithm that is called heuristic search. Heuristic search. Okay. So wait for a minute. I am coming. So we have a heuristic search actually. So what exactly we are using here? So in a simple search, we are just using the searching technique. But here what we will use, it's a combination of knowledge search, knowledge based search. Okay, knowledge plus the simple search, what we have discussed now. Simple search. So it is like a hybrid model. So in starting, I told you when I was discussing this part. Sorry. So here I told you that searching is one thing, and this is another knowledge based search is there. Okay, so what exactly we are doing here, we will merge with knowledge plus search, and it will give you is equal to heuristic search. So both the technique we have merged. Okay, and it's a hybrid model of so the heuristic search is a combination of knowledge plus search, simple search. So that is called heuristic search. What is the meaning of knowledge here? So for searching, we will use some type of knowledge, okay, available in our system. So what is the problem in simple search? So the complexity is the issue. Okay, to solve the problem, it's very difficult. So what we are doing here, we will reduce the complexity. So there may be very simple question in your mind, how we are reducing the complexity. We are using knowledge actually. So on the basis of knowledge, we will try to throw away. So we will try to throw away some nodes actually. So we are not going to exploit each and every node here. So what we will do here, we will throw away some nodes. How it will be possible? It will be possible with the help of knowledge actually. So what exactly we will do here? We will suppose we are starting from one node. Okay, suppose I have a node here, and the heuristic value we will find out actually. So we have a heuristic function here. Okay, heuristic function will be there, which will give the heuristic value to us. Heuristic value will be given to us somehow. Okay, and suppose it's 100. Okay, and the goal actually, ultimate goal here is to achieve this value 10. You want to achieve 10. So this is your goal here, and this is your state, first state. Okay, so you have a function. Okay, through that you will calculate the next state. Suppose next state you got here 80, and here you got 90. Okay, at this place 90. Here you will use the knowledge. Knowledge means you know that 80 minus 10 is 70, and 90 minus 10 is 80. So I'm giving very basic example here. So here you know that which solution is very near to the goal state. So what you will do here, you will discard the another node. So here I will discard this node, and I will continue with this node. Okay, so I'm not going to exploit this 90 node again. So suppose again here I have 70, and I have here at this place 60. So again I will use the knowledge. I know that 10 is here, 70 minus 10 and 60 minus 10. So what you will do, again you will discard this node, and then you will continue with this node. Okay, so like that you will continue. Here you suppose you got 50, and here at this place suppose you got 40. So again you will discard 50 and you will continue with this node. So here you can check the complexity. Here I was exploiting a single node. Here I am exploiting a single node. Here I am exploiting a single node. Here also I am exploiting a single node, one. So here you can check the complexity actually. So if it will be the simple search technique, so you can check the complexity. Here you are exploiting two nodes. Again here you will exploit four nodes. Again here you will exploit 8 nodes, and 16, like that you need to exploit. So definitely this heuristic search, when you are using some knowledge in heuristic in this simple search, so definitely it will reduce the complexity. Time complexity will reduce. Okay. So, and what we are doing here, so if suppose I want to write the pseudocode for this algorithm, so what you will do, so you have the open domain here, and in open domain you will use some sort of knowledge. Okay, and then you will put the new nodes in this one, and how you will proceed here. So while next is better than current, so better than current, so on which node you are now actually currently. So when you have a next node with you, so you will check that next node should be better than the current. Only then you will update this next node. And how it will be? It will be like best. It should be best. And then you can move with the help of current node. So you will check on the current node, okay, move, and then you will check which one is best. Okay, suppose current node are two here, so you will check move one, move two, and out of them one and two, you will check the best. Okay, and which one is best, that will be updated by next. Okay, so next is better than current means the heuristic value should be high or low. It depends on the application part. Okay, so this algorithm, because of this property, is called hill climbing algorithm, because we are saying here that next should be better than current. So this algorithm can be considered as hill climbing algorithm. Why I am saying hill climbing algorithm? Why I am saying hill climbing algorithm? That this is an hill climbing algorithm. So suppose actually here, suppose I have a hill is there. Suppose this is the hill actually we have, and one person is there who want to move on this hill actually. And here suppose he is on the ground, so the value of the is 0 0. And when you will calculate at this place, suppose it is like 2 1 or whatever. So according to this algorithm, you will select the best, and you want to reach on the top of this hill. You want to reach on the top of the hill, it means you are not taking any negative. Suppose any value is here at this place, that is negative, okay, -1 or something else. So this value you can't consider here at this place. Okay, this is not required because you want to reach on the top of the hill. Okay, so better than current you will choose. So it is 0 and it is 2. and you know that for climbing a hill, this is better actually. Okay, you will be here. Again, you will check here 5 or whatever is value is there. So again, you will check here, and then you will be at this place because all the values are greater than to the current. Again, suppose this point is 6 here, and here it is 5. So you can't be here because according to the problem, the 6 is better than 5. Okay, if similarly you want to reach at the below of the hill, then you will take this value and you will be here at this point. Okay, so this is the reason actually. This algorithm is called hill climbing algorithm. But here also at this same place it has the problem actually. Suppose this person is here, and then he will see that this is the highest point actually. This is the highest point, and his aim suppose want to reach at the highest point. His aim was to achieve this highest point, but the algorithm, your algorithm is here now at this point, and he will check that this is the highest point, this is not the highest point. Now your algorithm will not work actually. This hill climbing or this heuristic search will not work because this 5 it will not touch, 4 it can't be there, and 3 it will not be there. So it will work in one direction only. Okay. So you will check from here that this is the highest point, but you can't be there anyhow. So what is this actually? This is called local maxima here. And this is called global maxima here. Global maxima at this place. Okay, and anyhow you can't be at this place. Okay, and this is the disadvantage of heuristic search. This is the disadvantage of heuristic search. So it is not true only for local maxima and local uh, global maxima. Suppose you reverse the problem, means from hill you are on top and you want to be at this place. So you will check that which point is less than. So you will be here simply, easily. Again, suppose you have a point here like this at this place, and you can't be here at anyhow because you are here at this point now. Okay, so because sorry, you want to come on this side. You want to be at, you suppose you are here when you are coming from the hill towards the earth. So you will be here, and from here this is the point 0 0, and from here it will start some positive point, and your algorithm is working in reverse mode, means you are going to the minimum side. So this is the minimum value here. From here some maximum value will start and your algorithm will not work, but the global minima is here. So you can't be here anyhow. This heuristic search will not work here, and this is called local minima. So I think you have heard about these terms, okay, but it will be clear today that what is the meaning of these algorithms, these terms actually. Okay, so this is the problem associated with heuristic search, but it's not like that the heuristic search will never work. Okay, so I have an example for you, and you can check this example. So I will show you how the heuristic search can work and how it can't work actually. So I will open the slides. So already we have done all this part. We have, okay. So this also we have done. This is heuristic search. Already we have done. So yes, heuristic search. I told you the problem also. So here I have a uh, example related to heuristic search. So what I have some destination part, okay, and we have some source, and I have a heuristic function here. Okay, so this is not working. Okay, so what let me discuss. So what exactly I have some blocks here, okay, like A, B, C, D, E, and this is my goal state here, A, D, B, C, and E on the table. Okay, so how I have designed the heuristic function, I am giving +1, okay, if it is on the correct position according to our goal state, otherwise -1. So E here is on the table, and E here also is on the table. So what I have done, I given +1. C is on the table in our goal state. C is here on the table. I have given +1. B should be on C, and B is on C, so I have given +1. A should be on D. No, D should be on B, but D is not on B, so I have given -1. A should be on D, but A is on B, so I have given -1. So what is the value? Suppose this one +1, this, so I have +1. So the total value here is +1 in this case. Okay, from this state. So now at a time you can move a block. Okay, so you can move on D, you can move on table. So like that chances are there. So you can move the blocks here. So I have moved A onto D. So this is my next state here. A I have done here on D. So again, you need to check the values. So it is +1, +1, +1, same, but here it will change because A is on D, A is on D, so it is +1 and it is -1. So this one will cut that down, and it remaining all values will be there. And what it will give you? It will give you +3. Okay, another chance. What is the chance? Another is you can move this A onto now D onto A. Okay, D onto A. So I have moved this one here. So this +1 will cut this +1, this one, and I have total +1 from here. So this is my next state from here. That is also +1. Okay, another move you can do. What you can do here? You can shift this A onto the table. A onto the table you can move. So it is here. A is onto the table. Okay, and it will cut this value, and this one will cut, and it will give you +1. So it will also give you here +1. Another chance, D can be on the table. This D will be here. So it is there. Okay, D shifted here, and you can check this value and this value, and it will also give you +1. So if I will give this heuristic value here +1, +1, +1, and +1, so the total heuristic value is 5 from here. Okay, and here this, if you will check which one is very near to 5, so this is not very near, this is not very near, this is not very near. So this is the only state which is very near. So I next iteration I will consider this state. I will not take this one, I will not take this one, I will not consider this one. So this is an example of heuristic search. Okay, so I will start from here. So what you can do, you can shift this A onto B. If you will shift A onto B, the same state will be there, and it will give you +1. it will give you +1. Another chance, A you can shift onto the table from here, and this state will be there. So this state will be there, +1. Another chance is you can move B onto A here. Okay, so B onto A. So this is a different state, and when you will check this state also, it will also give you +1. It will also give you +1 here. So it is +1. And another chance is there. So what you can do is you have shifted there. B you can put onto the table. So B I have shifted onto the table here. So this is the state. So you can cut this one, you can cut this one, and it will also give you +1. And here you will stuck actually, because all the solutions are equidistant from your answer, actually the goal state. So this is +1, this is +1, +1, +1, and from here you can't proceed anyhow. You can't proceed. Okay, and your algorithm will say that +1 is the answer. And this is the problem with heuristic search actually. So local minima and local maxima. So why this problem is existing actually? So okay, we'll discuss why this problem exists, but I will show you the, if you will change the heuristic function little bit, means if you have a intelligent heuristic function, then you can solve this problem also. So what I will do here, I have done add 1 for every block in a correct structure that the block is sitting on. Okay, so and subtract 1 for every block. The same problem, I have the same problem here. So what exactly I have done here, so you can count the story. So this is E on table +1, C on table +1, B was on second +2, D is on third +3, A is +4. So total value, heuristic value is +11. Similarly here, so directly we will check the block number and is it correct or not. E on table, and it is correct according to your goal state, +1. D is on second block and it is not on correct, -2. C is incorrect, +1. B is correct, +2. A is not correct, -3. So the heuristic value it will give you is -1. Now you can shift. Similarly, A can be here on the D. So it is on D here. And then you can calculate the values. It is -3. It was -3 here, -2. And it will give you -1. So it will give me -1. And again, you can shift this D onto A here, and it will give you -3. It will give me -3 here. And then again, I can shift this D onto the table. D is onto the table here, and it will give me the heuristic value is 0. Okay, and A I can put here onto the table, and it is onto the table, and it will give me +1. Okay, so this is the possible states, and +1 is very near. So I will discard this one, I will discard this one, I will discard this one, and I will consider this particular state for next. So I will discard, I will discard. Okay, and what you can do now, you can shift B onto A. Okay, one possibility. And when I'm shifting B onto A, so this is the my state here, and it is giving me -5. So I will write here -5. Okay, and then I can shift this B onto here, D, and it is giving me -4. minus 4. And you can do B onto table. B may be onto the table here. So that is there. So B is onto the table here, and it is giving me minus 2. Another chance is you can put D. Okay. Okay, this is the minus 5, minus 4, minus 2. So I put D onto B. D onto B here. And it is giving me plus 6. So this is the total possibility here in this case. So I will discard this one, I will discard this one, I will discard, and I will proceed with this state. And here you can check if I will put this A onto D, and it will give me plus 11. So I have the solution here. Okay, for the same problem. In last, we have stuck, okay, in local maxima, but here you have the solution. So if you can change the heuristic function, sometime it will provide you the solution. Okay, and heuristic search can solve so many problems, but sometime because of this problem it can stuck somewhere, and then it will give you the wrong answer. Why it is giving the wrong answer actually? So the concept is very clear actually from here. When I was discussing this part, so what I told you that you have a node here. Okay, you have here, you will discard this one, then again you are here and you will discard this one, again you are here and you will discard this one, again you are here and you will discard one node. Okay, so what exactly is happening? Suppose this is 100 value and you want 10. So what, when you are discarding this 90 point, okay, and you are going with 80, so the chances are there that somewhere when you will exploit this 90, the 10 was there, but because you have discarded in starting only, so somehow or anyhow you can't be here actually, you can't be here at this point. So because you are searching in this domain, so that is the problem actually here with this algorithm. So you can't be here at any point actually, at anyhow. So that's why this is the issue is there with heuristic search. Okay, so to remove this problem, we have very powerful techniques are there. So that is meta heuristics actually. We have meta heuristics with us. So what meta heuristics are? To remove the problem of local maxima and local minima, some meta heuristics algorithm, okay, are proposed which uses heuristic search iteratively. Okay, so what exactly we are doing here? Suppose you are here, so you will discard this point, you will discard this point. So here we will generate new points. So when you are going here, so we will try to exploit these new points and somehow we will try to find out the correct solutions. Okay, so that's why we have meta heuristics techniques with us. So this is not nature inspired algorithm actually, it is inspired by genetic algorithm. So it was introduced in 1995 by Stone and Price. So it is a little bit different from genetic actually. Genetic is different, but the idea is same here, but it is totally different. So here what we exactly will do, we will try to generate new vector by adding two weighted difference of two vectors to third vector. Okay, and then mix new vector with target vector to yield a trial vector, and then we will replace the target vector with trial vector. So let me discuss in detail because it is not. So here what we will check this condition. Okay, it is not for max generation. It may be another condition may be there. Okay, number of iterations sometime we will check. So when you are achieving the number of iterations, then you can stop. Okay. Sometime we are checking number of value only. Okay. Sometime maximum generation. Okay. So you will do here mutation, then crossover, and then selection operation. Okay. And here you will generate the new population again. After generating again, you will check. Okay. And then again you will go in this process, and again you will find a new population. Again you will, so like that your solution will filter. Okay. By iteration, it will try to achieve the correct solutions in materialistic technique. So what we have here to optimize a function for dimension d, we want to. Okay, so solution space is like that. P is equal to x1, x2, xnp. So this x1 is not a single value actually; it is a total vector. Okay, when we are saying dimension d, x1 g will be written like this: 1, 2 till d. Okay, x2 again will be written like this: 1 till d. X and p again, that many values will be there, 1 to d. So each value here is like a vector actually. So these algorithms are to solve very complex problems actually. Okay, so that's why this population is also having a large number of values here. So here I have written this xig is xig x2 till xdg. So that's why this is not a single value here. Okay, it's a complete vector. So this is I is equal to 1 to np, number of populations, and g is the generation number. So how you will initialize the population? So we have some x lower value here in the domain, and we have some x upper value. So what, suppose x lower is 0, x upper is 5. So this is the domain here. Okay, 0 to 5 and 5. And you want to create all the values in between 0 to 5. Okay, it may be minus 5 to 5 also. So then it will be grow like in this way, this fashion. Okay, from here to here in this fashion. So here I want to initialize the population. So I have a simple loop here for dimension, and this x lower, suppose 0, x upper is 5 minus 0. I have random value here, suppose it is 0.25. So what it will give you, it will multiply, and definitely value will be between 0 to 5. Okay, so like that, on the depending on number of population and number of dimension, that many points will be created here in domain. Okay, so random is like uniform random number between 0 and 1. Okay, so like that you will create the initial population is there with you. So x you have created, x you have the target vector is x here. So that is there with you when you have initialized the population. So now here I will do the mutation in this case, and mutation how I will calculate. So this is my donor vector here. This is my donor vector. So VIG, I'm saying XR1G plus F XR2 minus XR3. So what exactly we have when we have created X? So they have like XR1, sorry, X1, X2, X3, like that we have. Okay, in X1 again, I have this X1, sorry, 1, 2, 3 till D. X2 again, I have like 1, 2 till D. X3 also again, I have some values 2, 5, and like that. So what exactly I'm doing here? So I will take some value from here, X1, XR1. Okay, R means random value. So it is not X1 actually. So R1, R2 and R3 will be randomly selected and they will not be equals to each other. So what it may be like, it may be x5 plus f x7 minus x8, because r1 is 5 here, r2 is 7 here, and r3 is 8 here. Okay, so this like that one more vector will be created. Okay, and it will be different from your existing vectors. So Vij is called mutant vector here. So f is a scaling factor here. Okay, so what is the meaning of scaling factor? So it will try to control the amplification. Control to amplification. Amplification means sometimes the values will go beyond the domain. Okay, not control, actually it will try. Suppose this is like one value is 5 here, second is, suppose this is where the f is existing between 0 to 2 or 0 to 1, sometimes suppose it is 0.5. Okay, this value is here, suppose 2, okay, and minus 0, like that is there. So if this scaling factor is not there, then it will give you 7. Okay, suppose this is 4, sorry, 4 plus 0.5, 2 minus 0. Suppose this scaling factor is not there, so it will give you 6. And your domain is from 0 to 5. But if it is there, 0.5, 2 minus 0, then it will give you 5. Okay, so it will try to control the amplification, but it will not take the guarantee. Sometime, like here, and I'm writing this equation, so it will give you 6. The domain is in between 0 to 5, but still it is giving 6. So it may be out of domain, but it will try actually. So it is clear from here that it can control little bit. So I is not is equal to R1, is not equal to R2, is not is equal to R3. Okay, so if you want to apply differential evolution or DE algorithm, then number of population should be greater than or is equal to 4. Why? Because of this XR1, XR2, XR3. 3 value is required here. Okay, 1, R1 is not equals to R2, R2 is not is equal to R3. So that's why 4 vectors should be there at least. Only then you can apply this algorithm. Otherwise, it will not work. So after mutation, we will got this donor vector from here, or mutant vector. This is called donor vector or mutant vector. So it is having two names here. Okay. So F will try to control the amplification, and XR2 minus XR3 is the differential variation. So F is a scaling factor. Already we have discussed that part. Okay, this equation actually, when we are writing this equation here, XR1 minus XR2. So this is called the mutation strategy. Okay, so D, E, and 1. So I will discuss this part also. So this is over. You have created target vector X. You have created donor vector V. So now we will come to the crossover part. Okay, and here I will try to find out a new vector, that is trial vector. Okay, sorry, that is trial vector. I will try to find out. Okay. Yes. So how I will code this trial vector? That is U actually. So X I have, V I have. I will find out the U. So here I am using this technique. So what I will do here, I have V is there already with U. I have X with our this one. So I will follow these rules, and then I will choose randomly from here. Okay, and after doing some calculation, I will find out the new vector here. Okay, so I will use this one Vj. So first thing is, suppose you have here 1, here 1, here also you will do the calculation for 1. So that is the j here. Okay, j is for which vector you are doing the computation, j. and here also J. Okay, then I will create random J. It will be between like from 1 to D dimension. No, between 0 to 1. CR is a parameter here that is called crossover probability. Okay, and if it is a probability, then it is very clear that value will be between 0 to 1. Okay, and J is equal to J rand. So J rand, I will create a random value here which will be between 1 to the dimension of the problem. So okay, so let me start how you can do it. So this is all the nomenclature I have given here. CR is crossover probability. J rand randomly selected between 1 to D. Random number between 0 to 1. Okay, R is this rand J actually. This is rand J. And uj jth vector, vj jth vector, xj jth vector. Okay, so crossover probability CR will be selected by the user actually. So it's a parameter here. F scaling factor is a parameter, so very less parameter we have here, and CR is also a parameter, and it will be chosen by the user according to the applications. So here I have dimension D is equal to 7, J rand 3, and crossover probability 0.8. Okay, so for first vector I will do the calculation x1, v1, and here also u1. So random 1 for this I have created, that is 0.7, and it is less than 0.8 CR. So here you can check. This is the equation I have written here. So random 0.7 is less than 0.8. Correct? J is equal to rand. J is means if I am doing the calculation for first vector, and J rand is 3. So J is not is equal to J rand here. So that is very clear. But this is or condition, not required to check. So I will take from V. So first vector I will choose from V here. So V1 will be there. Okay. Now for second vector. So when I'm doing the calculation for second vector, I will choose x2, otherwise v2 for u2. So it is 0.91 and it is greater than 0.8, means greater than CR. So 0.91 is greater than 0.8. So this condition is true. And J is not is equal to J rand. So I am doing calculation for second vector and it is not equals to 3 for this value. So I will choose from here x. So I will take from x. Next, 0.8. 0.8 is equals to 0.8. So this condition is true. J is equal to J rand, yes. 3 is equal to 3 from here. So I will take this value from V, this condition. Okay. So V3 will be there. Again, this 0.9. 0.9 is greater than 0.8. So x4 will be there, this value. Okay, and like that v5, v6, and all the values we can select from here. Okay, so this like that we have this. This is my target vector, this is my donor vector, and this is my trial vector. So now in next we will do the selection, and in selection this vector is not required at all. Only trial vector and target vector will required. So I have some numerical values here so that you can check that how it will be there. So this is the first vector you have, this is the donor vector you have here, and this is my trial vector. This is my trial vector here. So this is my target vector. So it is totally different from this one. Some values definitely will be there, but in selection you need to check again. So this is I have done here crossover, I have done mutation crossover, So it is not like that only one technique is available for crossover. So many are there. We are not going to discuss each and every technique. So there are basic papers are there. You can read from the online material is there. Yes, one more thing is there, bounding of domain. So I was discussing with that part, that's 5 plus 0.5. Suppose it is 4 minus 1. Okay. So 5 plus 1.5 and it will be 6.5. So what is the situation? So it was the domain was defined between 0 to 5, but you have here 6.5. That is out of domain. Okay. So after this crossover, because after crossover, you need to make this 6.5 to 5. Why? Because suppose you are here 0. Okay. So and 5 is this side and this side minus values. Suppose 6.5 is there here. So what you will check? You will check the nearest domain boundary at 5. So this will be converted to 5. Suppose you have any value minus 2. You will check the nearest boundary 0. It will be converted to 0. So you can't work out of domain, okay, because that is not required. So I will decide according to the situation. If any value is exceeding the limit, then replace with upper bound. So 6.5 will be replaced by 5 and minus 2 will replace by 0. And this part you will do after crossover, because chances are there after mutation that chances are there you are not going to select that value which is out of domain. So once it will be final that the out of domain value is there, then you need to start this bounding of domain. Okay. So this is the algorithm DEXYZ. This is like the strategy actually. So this is the nomenclature. If you have single difference here, then you will use 1. Okay, if you have two differences here, you will use 2. If you have single and best, then you will write best here and 1. Okay, if you have best and 2 random values, and so it will be 2 and like that. Okay, now we will go to the selection part. So here the very easy survival of the fittest. So what you will do, you will take the trial vector, you will take the target vector, and you will evaluate the fitness on the function, heuristic function or the fitness function. Okay, you will check the values here and then you will decide that which one will take the part in next generation. Okay, then you will decide the so mutation, crossover, selection continue until some stopping criteria reached. Actually, you will see. So this is the actually we are merging in target vector. So this is my U, the trial vector, and I will put this value into fitness function. I will put this value into fitness function. So if this condition is true, then I will select from trial vector. Otherwise, I will keep as it is. Okay, and it will give me the next generation of vector. So fitness value you will check here. I have a very simple numerical example. So whatever we have discussed here, it should be like you need to understand how it is working. Okay, so I have population size 5, dimension is 3, f is 0.5 and cr is 0.8. And this is my function here, f x1 is square, x2 is square, x3. So we are not using simple functions to solve this problem, but here it is easy. So I need to initialize between 0 to 5. So randomly I took these values. So 4, 1, 2. So it is my x1. Okay, this is x2. This is x3. This is x4. And this is x5. So NP. This is NP here. This is one dimension, 2 and 3. So this is the dimension D. Okay, if the dimension is 30, you can imagine that 30 variables will be there in x1 only. If it is 500, then you can imagine the data actually here. Okay. So here I want to evaluate this function fx. So what you will do here, x1 square plus x2 square plus x3 square. So it will give you 21. 3 square plus 2 square plus 1 square, it will give you 14. 1 square plus 1 square plus 2 square, it will give you 6. 4 square plus 3 square plus 2 square, 29. 1 square plus 4 square plus 3 square, 26. So this function I have evaluated, and this evaluation is for target vector. So this is my target vector here. Okay, now I will calculate, I will apply mutation here. So I will take R1, R2, R3, X4, X1 minus X3. So you can check here, X4 is this 432. So I took 432.5, 412 minus 112. So after doing this calculation for X1, I have V1 here, and this is out of domain 5.5 because my domain is between 0 to 5 here. Okay, so this is out of domain, but we are not doing anything here. Okay, and like similarly, I will calculate V1, V2, V3, V4, and V5. So I'm not going to for all these calculations here. So I have done only for one, and only for one I will use here crossover. So for crossover, random 1 is 0.6, random 2 is 0.9, and random 3 is 0.7. Okay, CR is already 0.8 if you remember in my example. So 0.6 is less than 0.8. So 0.6 is like, this condition is true. So I will take from V. So V is my 5.5 here. So I will take 5.5. So this is my original vector X. This is my donor vector V. I'm doing calculation for single vector. Be very careful. Okay, for this second calculation, I have 0.9 greater than CR. So I will select from X1. Okay, 0.7 is less than, so I will take from here 2. So this is my trial vector here. Okay, trial vector at this position. So here, this 5.5 will be converted to 5 because I told you this is bound of domain. Because in next generation you are not going to do anything, so here only you need to make this change. So I have done the complete calculation for first vector, this one, r1, r2, r3, then donor vector I have seen this one, and this one also you have seen. So this calculation we have done for all the vectors here. Okay, so you can take these variables similarly because unnecessary I want to do these calculations, but it should be clear. Okay, so this is my trial vector. So from now this donor vector is not required, only target vector and trial vector is required. So what you will do here, this is my target vector, this evaluation already we have done. Now this is my trial vector 5 1 2 3 3.5 1.5, and here I need to evaluate that function is there na fx is equal to x1 square plus x2 square plus x3 square. Okay, so for this purpose fx we have done here. Okay, oh sorry, here it is there. I will do fu. Okay, so what you will do, 5 square plus 1 square plus 2 square. So it will give you 30. 3 square plus 3.5 square plus 1 point, it will give you this one. 0 square plus 2 square, it will give you this one. 1.5 square plus this one, and 2 square plus 4.5 square plus 30.5. So now you will do the selection. So 30, 21. 21 is less than. So I will take from here this vector. 23.5 I will compare with 14. So I will take this vector here as it is. 10 and 6, I will take this vector as it is. 4 and 29, so I will take this vector from here. Okay, 30 and 26, I will take this vector here. So this is my new generation, new population actually for next iteration. It will change again and again. So in each and every iteration it will change, then fitness will change, and like that it will try to iterate on the basis of this condition actually. Evaluate fitness, and like that it will go. So this is the about the one algorithm, and here this is the application part. So when the this DE was evolved, that time the researchers are working on strategies also. But now this area is exhausted and there is no chance to work. But we have implemented one strategy that time. And there are some standard functions if you want to check these algorithms. The very difficult functions are there to solve. So you can solve. Okay. This is the second application here. So what exactly we are doing here? The OTSU method was there. So image segmentation. Gray level images. You can segment. So we have used this function with DE actually to solve the segmentation problem, and everything was available. And then just function we have took, and we have done some modification in DE also. So we have developed another algorithm, a variant of DE, and then we work with OTSU method. Okay, that time. So this is one application, and this is another application here. So here what we have done actually, we have developed our fitness function actually, and this is the work which is always open to all. So if you can design the mathematical, you can model your problem mathematically, you can design a fitness function, then it is very good actually, and you can apply these algorithms. Okay, so here this work we have done that time. And we have done in color image enhancement also. The same algorithm we have used there to optimize. Okay, so for data clustering, and not only for data clustering, recently we have done this an evolutionary block-based network medical image denoising using differential evolution, and it is this paper we have published in Applied Soft Computing. Okay, so these algorithms having actually so many applications are there. Okay, so this is all about the today's lecture. If you have any doubt, you can ask me.